So the primary form of substitution is actually what we just did with the trig substitution. Very specifically, let me just put a sort of a generic problem down. If we had something of the form, let's say, x squared over 9 minus x squared. I'm not interested in what the final answer here is. I'm interested in how would I attack this problem. You'd say, well, which substitution would we do? Sine, tangent, secant. We do the sine. So what would we let x equal? Very specific.
9 sine? Or no, 3 sine.
Yeah, because 9 is actually 3 squared, right? So it'd be 3 sine. By the way, does it matter what letter or what symbol I put here? No, just as long as it's not x. And sometimes we make the mistake of putting an x, which means nothing you say from that point on is true, because there's a high probability that there's no solution to that. You say, what do you mean? Because if I put let x equal a trig function of x, if they intersect at all, which is no guarantee, they may only intersect at one point, which means my answer is an ordered pair, not an antiderivative. All hell breaks loose at that point. Okay, you guys know what happens next, right? Dogs, cats, yeah, the whole thing. So I'm going to do this. So now my numerator is going to become the square of 3 sine, which is 9 cos squared. My denominator is going to become 9 minus the square under the square root, and then my this guy, okay? Now, I don't know what the answer is, but I do know that I'm going to get mass cancellation all over the place. Do you agree? And I'm going to get something that's probably relatively simple. And in the end, I'm going to substitute back to x because the antiderivative of a function of x should still be a function of x. Okay? You did that in Calc 1 when you did U sub. But the point is, I'm doing the substitution in this direction. I don't need a chain rule factor pre-existing in the problem. I'm creating the chain rule factor by going this way. That's kind of a nice thing. So let's take one that we know how to do. This is a very simple Calc 1 problem. Very simple Calc 1 problem. And I'm going to walk you through something that's going to be kind of eye-opening because we're going to look at so many different types of problems today. There is not a one-size-fits-all for what we're doing. In fact, every problem we do is going to feel very, very different. But the big picture is my strategy is going to be very similar. So what would we do in Calc 1 here? What would I let u equal?
X to the third.
And then my du is
3x squared.
3x squared dx. Well, I don't have a 3x squared. Okay, now I do. By the way, there's many of you want to manipulate that and play with it. That's actually mathematically impossible. You cannot manipulate this because du is not a quantity. It has no algebraic property. Dx is not a quantity. It has no algebraic property. These cannot be moved. They cannot be multiplied. They can't be touched. As an absolute, I feel really bad if your Calc 1 class didn't make this absolutely clear. If I don't have this exactly in the problem, I cannot continue with this. For example, if that exponent is not the right exponent. But constants, we know the integral of a constant times a function is a constant times the integral. Constants I can move in and out. So now I have my substitution. By the way, what I'm showing you is the only way to do this that has ever existed with U sub. And many of you do it completely different. Go, but I got the right answer. Actually, you have a wrong answer often because you'll have a U and an X in the integral at the same time, which completely changes the meaning of the problem and doesn't equal whatever you got as an answer, which means you actually have to make a series of major boo-boos. I don't want you to make any major boo-boos. This one's just too simple. So do we agree that this is now an easy problem? Yeah, this was why you loved U substitution in Calc 1, because this was just so slam dunk. This has no antiderivative as stated, because you have about 20 antiderivative formulas that say, if it looks like this is the antiderivative. But you don't have any function that's a product of cosine and something else, so that's why you did the U sub. Now it looks like something you know. You say this, and then you substitute back because my answer is a function, not a scalar. Remember, if I had given you limits of integration, you don't change back, ever. You don't ever change a variable in a definite integral and then change it back because you just evaluate that variable, right? You change your limits and then you evaluate it. It's exactly half the work. But in this case, I've got this. Great. Okay. What if I attack this problem the way I attack this problem? I don't mean as a trig sub, I mean as a let x equal. Well, let's start it the same way. let's start it with, let's let u equal x cubed. That's a good starting point. And if u equals x cubed, then what would x equal? You don't like this. By the way, don't use a root, use an exponent, it's easier. So u to the 1/3. Then what is dx?
The 1/3 u to the negative 2/3.
And then du. Okay. Let's pretend we didn't even see that there was a simple u sub there. It went right past us. Okay? So now my integral of cosine of x cubed x squared dx is going to equal the cosine of u. What do I do with x squared? Well, won't it be the square of this? What's the square of u to the 1/3? Be careful, there's rules of exponents here.
U to the 2/3.
U to the 2/3. And then dx, which is now what? 1/3 u to the negative 2/3 du. Look familiar? Every u sub you've ever done in your entire life, you didn't actually have to do a u sub. You could have done this way. Now, that's practical. That's pretty straightforward. That's pretty fast. This probably took a little bit longer, but the point is, I can always do this. What if? What if that was not an x squared? What if that was x to any other power but 2? Could I do a u sub? No. Could I still do this? Yeah, in fact, that's how you would do the problem. That's the only way to do the problem. If I don't have the exact chain rule factor I want, I introduce the chain rule factor. Yes?
Forgive me if I'm the only one that's lost, but back on the first problem that you did, when x equals 3 sine of theta, why then do we have 9 cosine squared theta instead of 9 sine squared theta in the numerator?
Oh, no, good catch. That should be that should be sine squared.
Oh, okay, cool.
It's me not being able to see that far away. By the way, if you are the only one who saw that, that's probably not good.
Okay.
Yeah. And now, the whole point on this one was we can manipulate this and we know what to do, and it's going to be something short and sweet. But it was really all about this type of substitution. Now, if you were doing this problem, yeah, do a straight up u sub. You already know what to do. That's not even the question. But what if it isn't exactly the chain rule factor you need? Which, how often will it happen that it's not the chain rule factor you need? Like 99.97% of all problems are not going to be u substitution. Between now and the day you die, if you do calculus continuously, you're going to have a few u subs. You'll have a few. I don't know how many, maybe 8, 10 more the rest of your life. No, they just don't happen. They happen in Calc 1 because we're learning how to integrate. They don't happen in real life, right? Problems that present themselves don't just magically have all the right chain rule factors sitting in the middle of the problem. So let's do a different problem, okay? If I asked you to integrate the sine of x dx, life is good. That's just this. Man, that's piece cake. But like I point out to folks, what if the question was sine of f of x dx? Could you integrate this one? And no, the answer is not negative cosine of f of x. Unless f of x is x, right, you can't just integrate this one. In fact, if f of x is not a scalar multiple of x, I may not be able to integrate this one at all. What if my f of x is log x? What if it's e to the x? What if it's tan x? Well, think of any function. No, you can't integrate it. There's no antiderivative formula, but there may be technique. So what if, just for fun, because that's kind of the primary goal today, let's put a square root of x in there. Now, I really want to do a u substitution, can I? Well, what's the only choice you would have for u?
X.
Not x.
Sorry, square root x.
Square root x, because that's my argument. Remember, your u substitution is if your argument isn't just x, then that's your substitution. So I would start by saying let this, then my du is 1 over 2 root x dx, which I don't have sitting here. Can I just introduce it in it? No, it's a function. You can only do that with numbers. Well, we're kind of dead in the water. Well, no, we can't do a u substitution. And again, I emphasize this even in Calc 1. U substitution is if I have the chain rule factor, or at least a scalar multiple of the chain rule factor as part of the integrand, I can do a u sub. If I don't, it doesn't mean I can't integrate the problem. It means I can't do a u sub. That's all. It just means I can't do that. But it doesn't mean I can't do the problem. Let's do this one exactly the same way as we did that one. In other words, yes, I want this to be true. So therefore, what would x be? U squared. So what would dx be?
2u du.
And here's the beautiful thing. Now, don't do this. But if I just said for fun, let x be, I don't know, e to the u. Okay, why would I put an e? No, I don't want to put an e in there, but just for fun. What if I did that? Well, then dx is e to the u du, and I would make the substitution, and I could write a new integral, and it would absolutely be correct. I might not be able to integrate it. I may have just made it a lot harder, but literally anything I choose here is fair game, believe it or not, as long as it's continuous. Anything I choose here is fair game. So obviously there are better choices than others, agreed? But anything you choose, because you don't have to have the chain rule, you're introducing the chain rule factor. That's the key. That's why this form of substitution is the dominant form. U substitution is very limiting in that if I don't have the chain rule factor, I can't do it at all. Whereas this one, I'm introducing the chain rule factor even if I already had it right there. So how do I rewrite this one then? This is going to be the integral of what?
Sine of u squared times
No,
2.
sine of, it's just sine u,
Oh.
2u du.
2u du. Wait a minute. That doesn't look scary.
Yeah.
How would we do this one? Integration by parts. This is a one-step integration by parts problem now. Didn't see that one coming, did you? Wow. And by the way, this is not only an integration by parts, this is the friendliest version because I don't have an exponent on that u. Now, I can't use u and v, so let's use, how about w and v? I kind of need different letters of the alphabet, don't I? So how about we let w, I'm looking at this guy, if you want, equal 2u, and then dv is sine u, du. dw is 2 dw, and v is negative cosine u. So let's see if this works. So I'd have negative 2u cos u minus the integral of negative cos u. Well, this is pretty simple, huh? So what have I got? Oh, that's a toughie. Integral of cosine.
Sine u.
Yeah, how about sine u? We're done with the calculus. Not quite done with the problem. Why?
Substitute the u's
Yeah.
back for the.
Yeah. So, what's my final answer then? Negative 2 square root x cosine square root x plus, I think I lost it. Sorry, I lost a 2 here. I think there's supposed to be a 2. Yeah. Yeah, there's a, make sure that one gets there. So there's a 2 there. So plus 2 sine root x. That wasn't easy, but with the appropriate substitution, we created an integration by parts problem that was, as integration by parts problems go, low level. Wow. Now, would you say that answer is pretty ugly? I want to check my answer right now. I'm pretty sure I did it right. I would check it through differentiation. That's going to be a long one, isn't it? I've got chain rules, I've got product rules, I got everything else. So here's where I cheat. I just go to Wolfram and say differentiate this. Remember, the whole point of this problem was your ability to integrate. But you can't check an integral except by differentiating. And just for fun, I did this one earlier on Wolfram, and I got an answer with a complex coefficient and the inverse hyperbolic tangent of a complex function. And it only gave one answer, and it was absurdly a bad answer. So I had done the problem by hand, and then I checked it by differentiating, and I got it back. So again, I love Wolfram. It's not very good for integrating. It always gives you multiple answers, and complex answers are kind of the main answers it gives, even when it's not a complex function. And the funny thing is, I am not aware of the existence of an inverse hyperbolic tangent. I don't know where that would ever come up. It's not a function you would ever see in any context in your entire life, because inverse hyperbolics are logarithms. So it's not a function that actually would exist in any context whatsoever. But that's what Wolfram created. It was kind of funny. Okay, but we were able to do this using this really basic substitution. So let's continue on this thing. Like I said, it's not a one-size-fits-all, but you'll see a strategy. Now, I'm not telling you to don't do U substitution. I'm just saying don't rely on it as your primary form of integration, because the farther you go, you'll realize it won't come up very often. I teach differential equations. Every single problem you're integrating. And we're in week 4. I'm not sure we've had a single U substitution yet. There's nothing wrong with it. We might have had one. Maybe, I don't know. But there have been at least a dozen problems that involved integration by parts, by the way. That's a very common all-the-time technique. Okay? That's kind of the one we use all the time, like I said. All right, let's do another one. Let's do, this one's kind of fun. I know I say that. It's kind of a weird thing to say. Yeah. Wow. Well, if that was just an x, then this is just a simple natural log. I can do that in one step. So is my answer just natural log of the denominator? No, because it can only be a log if the numerator is the derivative. Do you agree? So if my denominator is my u, my numerator would have to be the derivative, and I certainly don't see anything on top that would indicate that's, nope. No, so there's no u sub here in the classical sense. Now, I really don't like 4th root of x. I'd rather that be just a simple term. So why not start it like this? And this is usually how it begins. I'm not going to do a u sub, I'm going to let x equal. But I have to start somewhere. So if u is the 4th root of x, then what is x? U to the 4th. Then what's dx?
Four U to the third.
So does that mean I can go like this? Yes or no? Stare at that. Whether I can do this or not is not the question. This is now a rational function. And as an absolute mathematical statement, you give me any rational function, I don't care how ugly your coefficients are, I can always integrate. All rational functions can be integrated. It doesn't mean they're all easy. If my denominator has multiple factors, I might have to do a partial fractions decomposition. I only have one thing. But there is one caveat here. I can only integrate a rational function if, tell me about the numerator.
The numerator is smaller.
Smaller. And right now it's bigger. So what do I need to do? Long or synthetic. In this case, synthetic probably be easier. You can do the thing that the trick I showed you where you can add and subtract to the numerator, but unless you know all the terms from cubic on down, that might not be your best choice. I think synthetic for most of us would probably be the easiest way to attack this. So let's do this. Off to the side, I have 4u cubed u plus 1. What is my root? What is the root? Negative 1. Yeah, if I do plus 1, I'll get a completely different answer, right? What makes this 0, in other words? So my root is negative 1, and then my coefficients in descending order are what?
4, 0.
Just 4. No. 0u squared, 0u plus 0. I need all of those zeros. They're not just placeholders. They will determine my answer. The most common errors, there's 2 common errors. Getting the sign wrong here and not putting zeros in when they're required. Remember, it's always whatever your highest term is all the way down to the constant, even if you don't have one. So now, remember, this is where I learned many, many years ago from a student, this is where you mama the problem. You guys know what the mama stands for? Multiply, add, multiply, add. And this would be a mama problem, I believe. So what do? Multiply, add, multiply, add, multiply, add. That is my remainder. Okay? If that's a 0, that means it was factorable. This isn't factorable, obviously. So that means that 4u cubed over u plus 1 is equal to, in case you forget, That's the remainder, so the constant, the linear, the squared. So this would be 4u squared minus 4u plus 4 minus 4 over that. My fours are, I know, it's bad. My fours and my u's start becoming indistinguishable. So far, so good? I have to do this off to the side because I cannot integrate this as stated, but the new problem I'm about to integrate, 4u squared minus 4u plus 4 minus 4 over u plus 1. Easy, challenging.
Pretty easy.
That's pretty easy. God, I got a polynomial. So I just took something that looked absolutely impossible, made it something else that just looked ugly, and now converted that into something that's actually not difficult at all. Huh. All right.
Do you just factor out a 4?
You can, but yeah, doesn't really mean it. Yes, you could. I don't know that that's going to gain, you know, I'll just leave it in there. So what's the first one? 4/3 u cubed minus
2u squared.
2u squared plus 4u minus 4 log. Do I need the absolute value? We'll figure that one out in a moment. I may not, but right now I leave it in there because the antiderivative of this does involve an absolute value, but we haven't figured out if that can be positive or negative yet. Okay, so far so good? Oh, by the way, one of the reasons I'm not a fan of factoring out the 4 in this case is because then now I have a whole bunch of fractional coefficients, and I'm not sure there's an advantage. I would factor out a fraction, but I don't know I'd factor out an integer. So now I just simply substitute back. Now go really slow. I'm going to write it like this. What if I wrote that as x to the 1/4? That might make it a little bit easier. Because I don't know about you, but I'd rather not write roots. I'm not a big fan of writing roots of things to powers. It's kind of a tricky thing. Here's the exception. X to the 1/2, I'm going to write root x. But what if it's x to the 7/3? Do you really want to write the cube root of x to the 7th, or is it the 7th root of x? Oh shoot, which one is it? That's why I don't like doing that, because a significant amount of time people get them backwards. No, just leave it like that. The main reason you want to leave it like that is, if you were going to differentiate or integrate, don't you need it in this form? No, there's no advantage going this way, none at all. A simple rule of thumb is, whatever way is easiest for you to work with, if it's just a square root, I'll write square root. If it's just a cube root, I'll write cube root. But if it's more, So I've got 4/3 u to the 3rd power. I'm going to cube this. So what would that be? 4/3 x to the 3/4. It is absolutely correct to put the x cubed inside a 4th root. That is correct. I don't see any advantage whatsoever, and I can't check that. I got to change it back to the fractional. By the way, there is no priority between a fractional exponent and a root. One is not considered of a higher order or more simplified than the other. They're exactly the same. So in a calculus sense, we'd really prefer the exponent because, again, manipulation is much easier. Minus 2 what?
2x to the 1/2.
2x to the, 2/4 of 1/2. Now, so I'm going to put a square root here. Nah, if you're going to do fractional exponents here, just leave them fractional all the way through. Because what's now the next one?
4x to the 1/4.
And then finally,
4 ln x to the 1/4 plus 1.
now, x to the 1/4. First of all, x to the 1/4 can only accept non-negative input. Agreed? And when I take the 4th root, can I get back a negative number? No, so isn't x to the 1/4 plus 1 always positive? In fact, it's always at least 1. You all with me on that one? So is that acceptable in this case? What if that were a minus? Then this could be negative, right? If x was 0. So if that was a minus. Now, here's why I don't like a square root here. You have a fractional exponent here, here, and here. Why would I put a root here? Do you see that would make it kind of hard to read? Now, either all roots all the way across or all fractional exponents. I think we all agree that that's easier. That's the first thing I came up with. Because if I said I want you to check this through differentiation, that's a big yikes, by the way. Oh, these three terms are easier to, yeah, that one's pretty ugly, and there's a lot of simplifying, so that's why I'd go back to Wolfram and say differentiate this, and hopefully I got that back. Isn't that kind of nice? There's no way we could have done this using traditional means, but by doing this substitution the other way, let x equal something, this ended up being not a very difficult problem at all. It was actually, the calculus was easy. I had to do a lot of algebra first. And you're gonna find that's kind of a common theme. Now I want to do a similar problem that's a little bit higher level, because this one comes up and a lot of times we don't know how to attack the next one. So, what makes this problem particularly terrible is the fact that I have a root in the denominator. But I had a root in the denominator there, and it was a fairly easy thing to fix. You notice that I did not make, by the way, it would have been legal, but I did not make the entire denominator the u. I could have. By the way, that would have been absolutely correct. Do you know why? You want to know why I didn't make the whole denominator in my u? I'll show you. Because again, understand that all things are legal, but not all things are prudent. If I had made the entire denominator, then what would x have been? Which means to proceed in this problem, you would have had to actually raise that to the fourth power and expand it all the way out. I don't want to do that. I don't know about you guys. You say, but that's not that hard. Okay, instead of fourth root, let's make that, 10th root. Do you understand what I get? Did we have to expand anything? No. The exponent showed up here as opposed to on a binomial. Because if it showed up on the binomial, I would have had to expand the binomial. I don't want to do that. It's too messy algebraically. So that's why we did that choice. This would have been absolutely legal, but I would have ended up with this and it would have gotten really ugly really fast. So, do I pick u to be square root of x? Because that kind of leaves me hanging here. What if I pick u to be the cube root of x? Well, then it kind of leaves me hanging here. So neither one of those are particularly good choices. Can you think of a good choice of u that would kind of cover both? I think I heard somebody going wrong.
1/6.
How about 1/6? Huh. Then what would x be? The next would be u to the 6th power. Well, why is that good? Because then that would be u cubed, and that would be u squared, and I can deal with that one. Does that make sense? So this, I don't know if clever is the right word. You're more like you're being Sherlock, and there was a clue there. So I looked at a common multiple kind of thing. If you wanted to manipulate square roots and cube roots at the same time, you'd need to make them 6th roots in order to work with them simultaneously. So now what's dx?
6u to the 5th.
So let's see where this gets us. So this would now be 6u to the 5th. That would be u to the 3rd plus u to the 2nd. Oh, this is going to be like a big old, huge partial fractions econ. Oh, this is going to be awful, right? Well, can I get rid of some u's?
Yeah.
I can factor, or there's a much faster way.
Just get rid of the u squared from the numerator.
Well,
and denominator.
the problem with getting rid of is kind of ambiguous, because if I take a high school algebra student and say get rid of a u squared, okay. Is that legal, by the way? That won't get. I'm going to show you something that you may not have realized. And I say this all the time. Every algebraic step you've ever done in your life, you probably could do more efficiently. Every algebraic step I think that exists is either exactly one step or two. Now, we never do it in 1 or 2. We do it in 5 or 10 or 20. So it is absolutely correct to say this is 6u to the 5th times u squared times u plus 1. Agreed? And then I would have what?
6u cubed.
Over u plus 1.
Do we all agree that's where I want to go?
Yes.
What if I showed you there's a faster way? I never do this. Because most of the time there's gonna be a third step. Nope. I do this. That's what I do 100% of the time. Then it means I only have one step. There's never a second step, because the factoring is a step, and it's not an incorrect step, but you're going sideways. You're trying to determine what I have left over. If I just did this, then I've got 6u cubed over u plus 1. Same result, but in one step. And literally everything in your life that you had algebra, you could actually be more efficient. I could have added and subtracted the terms, but I think I would have lost everybody. That's too high of an exponent. So go ahead and just do the synthetic. Could I have done that using long? Of course. But long for most of us is a little more challenging, and we mess up signs more often. Synthetic's easier. Now, look at that over there. I'm going to move this way over here so we can see it. 6u cubed, u plus 1. That's not scary. In fact, my gosh, it's almost exactly the same thing, isn't it? Can we piggyback off that one?
Yeah.
I'm going to be really lazy. Isn't my answer just going to be instead of 4s, aren't I just going to have 6s right there? All right, let's be really lazy. I'm a big fan of lassitude. Okay. So what are we integrating then? 6u cubed. I'm sorry, 6u. Help me out here, folks. 6u squared. I can't see it, and that's why I make mistakes.
6u squared minus 6u plus 6 minus 6 over u plus 1.
Thank you. Yeah, I'm looking sideways. Well, we agreed a moment ago that last problem wasn't all that bad. So what is the antiderivatives here? Well, I'm not even going to have fractions this time.
Two u cubed.
We need more coffee in the morning.
2u cubed.
2u cubed.
3u squared.
3u squared.
6u.
6u.
6 log absolute value u plus 1.
6 log absolute value u plus 1. Now, by the way, the absolute value has to go there because I haven't determined the behavior of u yet. So you always put it there. It's your final answer. You're going to decide whether it's necessary or not. It's absolutely, no pun intended, it's absolutely necessary there because that's a straight up antiderivative formula. Now I'm going to substitute back, and like before, I think we want to leave it as fractional exponents. Let me, I hate doing this, but I need to get rid of some of this stuff here. So when I do this, I know I apologize, I get to a certain point, I know one of the professors always refers to this as the Mason-Dixon line. You got this little reference to the geography. Once you get any lower than this, people in the back of the room, you can't see it anymore, can you? Only the front row side. I try not to go much lower than this. Okay, that's why I bring it back up. So I'm going to have, when I make the substitution, what is it going to be? 2x to the 3/6 or 1/2 minus 3x to the 2/6 or 1/3 plus 6x to the 1/6 minus the natural log of.
Not the 6 in front of natural log.
Did I? Oh, thank you. 6, and then x to the 1/6 plus 1. Now, can x to the 1/6 plus 1 ever be negative? No. No. So can I do that? Yeah. If I left the absolute value, that's not wrong. But in this case, I wouldn't. I don't need it. Wow. Now, this one was a slightly higher level than the previous one because I had to be a little more clever with my choice. But based on my choice, it presented an integration that wasn't all that complicated. But you notice my integral is not one term. That's really the key. Calc 1, all of your antiderivatives, every single one of them. When you integrated something, the answer was one term. But now that you've learned things like integration by parts, oh, I'm integrating a product, but my answer is now a sum of things. I'm integrating one quotient, but my answer is a sum of a whole bunch of things. That's why it cannot be done in one step. Because if this could be done in one step, then your answer would have been just one term. What if miraculously I had the chain rule factor sitting on top? Well, then I could have integrated in one step and my answer would have been one function. That's the problem that's probably not going to happen very often. Okay. You guys good so far? Let's keep going. We got more fun. All right, let's see. Next, oh, yes, good one. This one was pretty awful. Okay. Now, I want you to notice specifically, where am I putting the dx? It's completely separate from the problem. A great many people put the dx in the numerator. The reason this is incorrect mathematically is dx is not a value. It can't be in the quotient. But if I can put dx in the numerator, then absolutely I can put dx in front of the quantity, which means I don't have to integrate the quantity. That's not a joke. If I can put the dx in front of the f of x, then you're going to integrate one dx and multiply your answer by f of x. A reminder, we know this, but sometimes we make a mistake. These are never equal. This is not part of the integral. I can't move this as if it were an algebraic quantity that could be commuted. So if I can put it in a numerator, then I made it an algebraic quantity, which absolutely means I can put it in front. Makes all integration really easy. Makes it incorrect, but makes it easy. So that's why I keep it separate completely. Otherwise, we get in the bad habit of treating it as a number or a value or a function when it isn't. And a lot of folks don't realize, I take a point, well, I left off the dx. By next semester, you'll realize the single most important part of that statement, the single most important thing, like infinitely more important than everything else, is this. The integrand is a distant second. The single most important part of this is the variable you're integrating with respect to, not the integrand. The instruction is I'm going to integrate something with respect to x because I can put any symbol here. These do not have to be the same. In Calc 3, you're going to understand that. In Calc 3, they are usually not the same because you're integrating with multiple variables. If I wanted you to differentiate something, I give you a function of x and I say integrate with respect to x, piece of cake. But if I give you a function of x and ask you, differentiate. I ask you to differentiate with respect to a different variable. Oh, that means I have a chain rule. That means it was a composition of functions. That means all sorts of other stuff happens. And my answer is not the same. It's completely different. So the most important thing is what am I differentiating with respect to? What variable? That's always the most important part. It's just in Calc 1 and 2, they're generally the same variable. But then you're going to learn next semester that from that point on for the rest of your life, they don't have to be the same variable. Why? Because you're going to have multiple variables in an integral at the same time. And you can only integrate with respect to one of them at a time. And it matters which one you're doing. That's why it's really important. And it's right now, it's just getting in the habit, a good habit. Man, the only possibility for an argument would be that quantity under the root, if I was going to do the substitution, right? Because it's the square root of something. That would have been so much easier if my numerator was in e to the x, wouldn't it? But it's not. In fact, it would have been so much easier if I didn't have the 1 plus. But I do. What do you think we should do here? I have stuff under the root. For me to do anything algebraically, I really only need one thing under the root. In your trig subs, didn't you always have a sum or a difference under the root? And by doing the trig sub, you now had one trig term under the root, then you can deal with it. So I pretty much have to make all of that minute. Now, I don't have a du. I'm not looking for a du. No, I'm going to let x equal, but I have to start with this. So, let's see. So e to the x would be what? U minus 1, so x would be by the way, that is very specifically not an absolute value. The only time absolute value shows up in a log is after you've integrated something. When you're moving back and forth, you can't make it absolute value because then you've changed the domain. That would be an error. Well, then what's dx? This is u minus 1, so the chain rule factor is a 1. That's an easy one. So it would be what?
1 over u minus 1.
Okay. Like I said before, any choice I make for x, I want x to be the inverse tan of the hyperbolic cosecant of t cubed, something evil like that. Anything I choose is legal. It doesn't mean the problem's going to get easier, but it's legal. But based on this choice here, I think I might be able to manipulate this somewhat. Okay, so with this choice in mind, let's start with the bottom. What will the bottom now be?
Square to u.
Square to u. I'm going to write it as u to the 1/2. What's the numerator going to be?
2 ln of u minus 1.
Well, isn't this e to the x squared? Isn't e to the 2x e to the x quantity squared? So what am I going to put here? U minus 1 quantity squared. That's e to the 2x exactly. And now I will introduce, ooh, I think I like that. Huh. That made it kind of good, didn't it? The fact that those exponents were not the same actually does not present a problem at all, as it turns out. We moved on from this one. Okay, so can we simplify that integrand? Well, I think the first thing we're going to do is that. I have u minus 1 over u to the 1/2. What is that equal to? I don't want a quotient. So u over u to the 1, break it up. So u over u to the 1/2 is u to the 1/2 minus 1 over u to the 1/2 minus 1 over u to the 1/2,
Which is
1 over u to the 1/2.
U to the negative 1/2.
How about negative 1? Boy, we are really not on our game today. Yeah, that's not the part we should be challenged by. That looks absolutely terrifying. Well, that doesn't. That looks kind of simple now. Now, it's all u-ish, but that's not an issue. It's something I can now integrate. Remember, the whole point of any form of substitution here is to create an integral that you can now integrate. If you could have integrated the original problem, would you have substituted? You just love substitution, so you'd have done it anyway, right? No, you don't substitute if you can do it, but you can't do the original one. But this one here is not bad at all. So what do I get? U to the 3/2, so times 2/3. U to the 1/2, so times 2. You notice what order I did it? I always get the exponent first, so then I get the coefficient. A lot of times people try to do the coefficient first, and they're looking at the wrong exponent. Now what? Substitute back. So this is what? 1 plus e to the x to the 3/2 minus 2 times 1 plus e to the x to the 1/2 plus c. Wow. Now, I got to do this. Maybe this is a problem that came up in physics. This actually is a problem that comes up in physics. And I got to do this, and I got to enter a whole bunch of numbers and stuff. That's pretty hideous, isn't it? This would be one of those where maybe it would make sense to factor, because of the fact that I have 1 plus e to the x happening multiple times. Here's the trick I'm going to show you. Don't factor this. Factor this. Factor before you substitute back, and I guarantee you 100% of the time it will be easier. Now, this is the answer. We agree. But remember, if I have to use this, if it's physics, you're going to have to evaluate that 30 times, right, for different values of x. You already know that. So you're doing this on your calculator, and it's taking you forever because you keep getting entry errors, and because you forgot to close a parenthesis, crazy stuff. So forget the plus c. If I were to just that guy. So what do I got? I think that's supposed to be, do I have that right? Oh, never mind. I was looking at the sign, making sure I got the sign right. I would certainly factor u to the 1/2. How about if I factored out 2/3 u to the 1/2? What would that leave me with? I'll do the first one. I'm sorry?
4/3.
If I'm factoring out the 2/3, then multiply that by 3/2. How about that? Easy. Just 3. Way overthinking now. Because 2/3 times 3 is 2. So here's the advantage. So now I have a final answer in the following form. U minus 3 minus 3.
When you take out the 1/2 from 3/2, isn't that u to the third?
If I take out 1/2 from,
You're looking at one.
are you talking about here?
The first one?
You're talking about right here?
Yeah.
You add exponents, remember? Yeah, don't factor the exponents, add the exponents. Now, this is the answer. I'm in a physics class where I have to evaluate this multiple times. I don't have to convince anybody, you already know what that means. You have something, you have to evaluate it many, many, many times maybe. Maybe x is time, and you've got to evaluate it at 30, 50, 100 different iterations. I've been there, I've seen it, I've seen people do it. This would be a little bit less taxing. Just a little bit less. That's the answer. But you might find this one a tiny bit simpler to work with if I've got to use it multiple times. But understand how it is. Here's the interesting thing. When I checked this on Wolfram, it didn't give this answer. It gave this answer. Now, I'd already done the problem, but it gave this answer along with like 6 complex answers, but that is the answer. But understand that it's legal to do this, and it is sometimes it's efficient. You never have to. Remember, you never have to factor an antiderivative, but if you've got an exponential or any transcendental function in general that the same one appears multiple times, we know that factoring it out often makes it easier to evaluate. That's all. It also makes it a heck of a lot easier to check. Okay? Let's see. I think I need the whole board. All right, we got another one of these. The next one's going to be a bit long. Part of the reason it's necessary for you to understand this whole process, you're saying, okay, I want to be able, real simple rule of thumb, if you're presented with an integral that has an antiderivative, by the way, most don't. You're presented with an integral that has an antiderivative, then you've got to be able to find it. You've actually learned, after today, you'll have learned every single integration technique that exists for one independent variable. There aren't any new ones. It's just practicing them, especially the ones that are more challenging. Next semester, you're going to be working with multiple variables. So you're going to have integrals that have multiple variables. And the question is there a version of substitution when you have multiple variables? Yes, there is. And it's a bit more complicated, but it uses the same premises we're using now. And so we get to that and we justify that one. It's really late in Calc 3. But you may have to do a substitution that involves multiple variables. So in other words, it's not let u equal x squared. It might be let u equal x squared plus y squared. Or something complicated like that. Yikes. So, which one do I want to do? I want to do that one. Now, I want to do the same thing. Do I want my whole denominator? Do I want my whole numerator? Do I want to just use e to the x? What do you think would make the most sense? Probably e to the x, because I have e to the negative x in there. So it would probably make sense to say, let's let our u equal e to the x. And part of the reason is because then this becomes u minus 1 over u. Everybody see that? Then that's u plus 1 over u. So if I do this, then what is x?
Natural log of u.
And therefore, what is the dx?
1 over u. du.
1 over u with respect to u. So this is going to be a fairly simple process, what we're doing next here. So I have u plus 1 over u I have u minus 1 over u, and then I'm multiplying the whole thing by 1 over u, integrating with respect to u. This is going to be a rational function. It's going to be a rational function. It isn't one yet. We've got to mess around with it a little bit. So you might say, okay, let's start by distributing the u on the bottom. That would be fine. If I distribute the u on the bottom, what will I have? In fact, let me take this out of the integral for a second. If I distribute the u on the bottom, then won't I have u squared minus 1 on the bottom? Now I have a problem at the top. There's only one thing I can do, and that's that. So now what's my top? U squared plus 1, and my denominator is, how about if I wrote it like this? Wink, wink. Actually, I should do a right eye wink. What is this integration going to involve? Partial fractions, yeah. But that's as friendly as it gets, right? 3 linear factors that are different. But this is, everyone see, this is going to be a partial fractions. I've created a rational function. So algebraically, this is equal to u squared plus 1 over u plus 1, u minus 1, du. Okay? I know exactly how to do this problem, and the degree of my numerator is 2, the degree of my denominator is 3, so I can proceed. I don't have to do anything clever. This is a problem that we've already done, and this is a problem that most of you have already done very, very well. This is not one that gives us trouble. So, off to the side, let's do the partial fractions decomposition. Clearly with a different color. So I've got u squared plus 1 over u plus 1, u minus 1, and that's going to be a over u plus b over u plus 1 plus c over u minus 1. Okay? When I put this all over a common denominator and I equate numerators, I'm going to get u squared plus 1 equals what? So when I put that over a common denominator, u plus 1, u minus 1, plus b times
U minus 1.
and finally c times.
U plus 1.
Now what I like about this is it doesn't matter how many factors I have, they're all linear. So this is the one where we can pick off 3 numbers and just wipe out the coefficients fairly simply. So what 3 values are we going to choose? How about 0, -1, and 1? So if I choose x equals 0 or u equals 0, then the left side will be 1, 0, 0, u equals 0. So 1 times -1 is -1 times a. Oh. All right, this implies that a equals -1. The implication symbol. If I choose u equals -1, then the left side would be 2. And the right side would be, let's see, if u is -1, 0, 0, -1 minus 1 is -2, times -1 is +2, times b is positive 2b. Yes? Good? Okay, good. I like this, no fractions. I'm always happy. All right, if u is +1, left side is
2.
and the right side is 0, 0, 1 times 2 times c. I like that. So that means this here is equal to the integral of, whereas a was -1, so it's -1 over u plus 1 over u plus 1 plus 1 over u minus 1 du. We good there? Seeing some faces. We did have one negative there, right? Only the A was negative. The rest were positive. Now, can we integrate this one pretty simply? I'm going to move over here because I don't want to erase anything. So, what is my antiderivative? First term?
Negative ln u.
Absolute value, because we don't know yet. Again, later we can look at this, but for now we'll put absolute value. Then what?
ln.
Plus? And then it's u, what's the next one?
Plus 1.
U plus 1, and then the last one is plus
U minus
u
1.
minus 1. There's a plus c. I got 3 logs. All of them have coefficients of 1 or negative 1. Can I squish them together as one log? When I'm substituting back, that might make my life a lot easier if I only have one logarithm. Sum of the logs is the log of the product. Difference of the logs is the log of the quotient. Can you write this as one log for me? Yeah. Is that right? Sum, they got on top, difference, he's on the bottom. Now, I'm going to substitute back, but you know, can I simplify this term right here greatly? Hugely. Off to the side, what is u plus 1 times u minus 1 all over u? Well, the numerator's u squared minus 1. So isn't that just u minus 1 over u? What do you think? You with me so far? Can we substitute back now? What did u equal? E to the x. So what's 1 over u? E to the negative x. And that's a minus, correct? Can this quantity ever be negative? All negative values of x, this is negative. Yeah, this is negative exactly half the time. To the right of 0, this is positive. To the left of 0, this is negative. Because if I'm to the left of 0, this is small, this is big. So I do need that. And there's our best answer. Oh, by the way, just you know, if I had made u my denominator, what's the derivative of the denominator? The numerator. So could I have done this in like 12 seconds? Yeah, I didn't want to do that though, because I wanted us to see this process. If you recognized your numerator was exactly the derivative of your denominator, I'd really want you to go with that. But why is this so cool? Because we didn't use that at all. We did this new version, we got it all the way to the end. This was a lot of algebra. This is probably more algebra than you're usually ever going to see in an integral. But the point was the process, not the answer. I wouldn't have had to tweak this very much to make it so you couldn't have done this. You know, I put a coefficient on any of these guys. I put a coefficient in any of the x's on top. You could not have done this simply, but this still would have worked. And we would have gotten a similar answer in the same amount of work. That's the beauty of this, is that it always works. It isn't always fast, that's not what I'm saying. So the idea is, if you're presented with an integral that has an antiderivative, you've got to be able to find it. It's that simple, because you now know every technique available. What about all the integrals that don't have antiderivatives? Well, we're going to tackle a lot of those later on in this course. We're going to come up with what's the bigger topic called asymptotic convergence. We're going to look at polynomials that act a lot like the transcendental function. I can come up with a polynomial. I can come up with 2 terms that look just like the sine of x as long as I stay close to 0. I show some of these in Calc 1. We're going to come up with polynomials that look just like e to the x for a while. So if I can't integrate the function I'm looking at, there may be a polynomial that's asymptotic to it that'll use that instead. This is how all of statistics works. All of statistics is based on this concept of asymptotic convergence, that it's never equal, but it's closing in. And so there's an infinite number of problems that we can't do directly, but we learn a back door. Okay? My favorite problem, you're going to hear me say this multiple times throughout this course, my favorite problem is we're going to solve a problem that actually has no answer. We're going to do a lot of those. We'll solve problems that actually do not have an answer because the integral has no antiderivative, but we're going to answer the question anyway. Usually it's definite integrals. Because in real life, you don't actually do indefinite integrals. We learn how to integrate in this class because what's the difference between an indefinite and a definite? How many steps? And it's the easiest step. I plug in a number at the end of the problem. That's not even math anymore. That's arithmetic. So an indefinite integral, I'm giving you an answer that's a function. The definite integral, I'm taking that and then evaluating the limits of integration. Our goal is to get the right antiderivatives. But in practice, how many are in physics? Do you ever do integrations where your answer is a function, or is it always a number at the end? If you think about it, for the most part, you're numbers. You're giving numerical answers. But you have to be able to integrate before you can do the numerical part. So what we concentrate on in calculus is the antiderivative. We probably don't spend enough time on definite integrals. Next semester in Calc 3, almost all of your integration is going to be definite integrals because they all have application. That doesn't make it a harder problem. It just means you're always going to do that last step. We have not done a single definite integral today. Had I put limits of integration here, is there any part of this problem you would have done differently? No, you'd have gone to the end and then evaluated it. No, okay. So that's why I'm not really concerned with that one all that much. Now, we're going to do one more. This is really the last of the techniques, and unfortunately this technique is not in very many calculus books, which is interesting because it may be the most complicated of all the techniques, but it is the only technique that works for certain types of problem. I affectionately call this the evil trig. Okay? What was trig substitution? I took things that were not in any conceivable way trig-ish, replaced them with trig functions, and it made our life easier, which sounds completely backwards, doesn't it? That you're going to replace algebraic things with trig things and it makes things easier, but that was the whole point. Because we had sums and differences of squares that worked out very nicely. These problems are going to be trig integrals that cannot be integrated. There is no U substitution. There's no let x equal kind of substitution. There is no trig identity. It's just wrong. Right? Everything about it just feels wrong. So the problem that I'm going to do, I'm going to write it down, but we're going to do it later. I want to do something like this. This doesn't seem all that terrible. Well, let's see. If I wanted the denominator to be the u, I'd have to have stuff on top, and I don't. Ooh, but unlike the other ones, if I call either tan or sine the u, then I have too many other things going. I'm not going to be able to do this using any of the methods we know. We don't have any method for this yet. This is why I call it the evil trig, because you have to learn the method, and the method only applies to trig integrals. By the way, they're always going to be quotients. If I give you trig terms, not in a quotient, you can always integrate. I don't even care if it has exponents. You just did that like 2 weeks ago. If I give you trig stuff, products, sums, doesn't matter. It's the trig terms in the denominator. That's what messes us up. Okay? Now, there are problems that we do know how to do, and we know how to do them very, very well. So, for example, what if I gave you something like this? This is something, I do this in Calc 1. I don't spend a lot of time in Calc 1 on this, but I do this in Calc 1. We cannot do this problem as stated. There's no function whose derivative looks like this. But can I manipulate this algebraically? Mm-hmm. Well, first of all, you don't like quotients that have trig terms in the bottom, but that's a 1 minus cos. So I want to show you because this looks very much like this on the surface. One I can do, one I can't do using just standard methods. The idea is what I might want to multiply this by? A conjugate. Yeah. You've probably done versions of this before. Well, if I do that, isn't that just sine squared now? not my favorite functions. I mean, I don't know about you guys, I don't love anything that involves a cosecant, but do we have antiderivative formulas for both of these? Yeah. That's the answer. It wasn't that bad. It wasn't that bad because we used triggish tricks. We saw a 1 minus cos, and we know that if I can make it 1 minus cos squared. Tell me where this problem would have fallen apart. Change one thing about this problem that we could not have done it. Tell me one thing about this problem. Tell me one thing about this problem that we could change to make this really terrible and not doable. And what do you think? Make it 2, make it anything else. Put any real number there other than 1 and you can't do this. Because that won't work over there, will it? It only worked because I had a 1. So if I replace this with anything else, now I can't do this one. And that's what we're going to learn how to do today. If I replace that 1 with any other real number, I still want to be able to integrate that. Because it doesn't seem like it should be that complicated, but actually it is. So let's embark on the evil trig. So I wanted to show this one because this one we could do. But if I tweak it slightly, we couldn't. Or if I put a coefficient in front of the cosine, for example. So this starts with the most unusual substitution. Let me make sure I wrote everything that I want down. This starts with a very unusual substitution. We're going to choose, now this is off to the side, we're going to do this later. We're going to let u equal the tangent of 1/2 x, which is totally weird, if nothing else. Now, think about the tangent function for a moment. Part of the reason for this substitution is what it does with our potential domains. Okay, this is one period of the tangent function. We know what that looks like, right? From negative pi over 2 to pi over 2. So here's what we absolutely know. We know 1/2 x has to be between negative pi over 2 and pi over 2, correct? So therefore, what does x have to be between?
Negative pi and pi.
Negative pi and pi. Well, that's kind of advantageous. You know why? Because that means on the unit circle, the angle of negative pi puts me here. The angle of positive pi puts me here. So that means on the unit circle, you don't think 0 to 2 pi, think any whole circle. This is going to be good for every possible angle except one. Only that one. That's a good thing, by the way. That means our domain is really big. That's a really powerful thing. Because I did it as a 1/2 x, it means x is between negative pi and pi. Negative pi and pi is every single angle except that one. Remember, if I had made this let u equal 10, then we would have only been good from here to here, half the circle. That's why that's a really cool thing. It's a very powerful thing. That's how we start the problem. Who figured this out? I don't know. But this is a very important statement right here. So if that's true, right off the bat then, let's see, I'm gonna do cosine first. Then what is the cosine of a 1/2 x? Here's what we're gonna do. Based on this substitution, we want to be able to state what the sine of x, the cos x, and the tangent of x are actually equal to. Because then the other 3 trig functions would just be the reciprocals. I want to be able to say sine x equals, tan x equals, cos x equals. So with that substitution, well, I know this is true. Secant squared is what? Secant squared is 1 plus tan squared. Can I say this? Well, that's secant squared under the root. Can I say that? Well, problem, there's a problem there. The square root of a function squared, isn't that generally always absolute value of the function? So am I running into any troubles here? Actually, I'm not. Why? Tell me about the cosine function between negative pi over 2 and pi over 2. I'm on the right side. Cosine's always what? The right side of the y-axis. It's always positive. Cosine is strictly positive here. So therefore secant is strictly positive. So do I need an absolute value? No. No, this is going to be positive. You're to the right of the y-axis. Remember, the angle is between negative pi over 2 and pi over 2. X is between negative pi and pi, but that's my theta. It's on the right side, so I'm always positive. So that's a legal move there. But then what does this equal? Huh. So the cosine of 1/2 x is exactly this. Okay? Now, we'll do a little bit of clever trig, not complicated trig. Sine, cosine, tangent, how are they related? Sine, cosine, and tangent, how are they related?
Sine over cosine.
So then would it be true that the sine of theta is equal to tan theta cos theta? Would that be true? Yes, no, maybe? Yeah, that's always true. So next, let's say then the sine of 1/2 x is equal to what? The tangent of 1/2 x times the cosine of 1/2 x. There's my tangent of 1/2 x. There's my cosine of 1/2 x. So what does that give me? U times this. Okay? U times 1 over the square root. Okay? So I've got sine, cosine, and tangent of 1/2 x. I don't think that's going to help me because you're never going to be asked questions where your argument is 1/2 x. So we now need to figure out how to get the x. Okay? Well, I have a couple of simple formulas. For example, isn't the sine of 2 theta equal to 2 what? Is there more?
Cosine?
Cosine. Yeah, it's called the double angle formula for sine. That's always true, isn't it?
Yes.
Huh. Well, if my theta is 1/2 x, then what's 2 theta? X. Ah, I think we figured out how to do the sine. So based on all the things I have here, wouldn't sine x be, I'll write it down, 2 times the sine of 1/2 x times the cosine of 1/2 x? Just using that double angle formula? But I have those sitting right here. So that would be 2 times u over square root of 1 plus u squared times, and the cosine was 1 over the square root of 1 plus u squared, and that gives me 2u over 1 plus u squared. And this is the first, I'm going to put it up here because I'm going to need the whole board. I said we need the sine, the cosine, and the tangent of x. We now have the sine of x. That was the first one we needed. So right here, the sine of x is 2u over 1 plus u squared. Now I need to get the cosine. How am I going to do the cosine? Well, let me remind you, don't we have a formula for this? If I replace cos squared with 1 minus sine squared, I know that's true. So therefore, the cosine of x should be 1 minus 2 times the sine of 1/2 x. Why am I doing that? Because I know that one. Right? This is the double angle formula for cosine. Kind of a strange use of the double angle formula for cosine. So this would be 1 minus what? Well, where's my sine of a half x? It's right here. Okay, I'm sure I got there. So what I want to do is square this. Let's prettify this. I think it's a word. So I have 1 minus u squared over, I'll continue writing it 1 plus u squared.
Did the 2 go missing after?
Oh, thank you. No, I don't want the 2 to go missing. Thank you. That would have ended badly. Can I put this over a common denominator? Well, that would be 1 plus u squared minus 2u squared all over 1 plus u squared, which is what? 1 minus u squared over 1 plus u squared. And that's our cosec's. We're never gonna, oh my gosh, the tan x is gonna be so complicated. That's gonna be so hard to figure out. What do you think? Or is it like right above this? Isn't the tan x gonna be this divided by this?
Sine divided by cosine.
Which is what? 2u over 1 minus u squared?
Yeah.
Oh, that's a good thing. Now here's what's crazy about that. When I get to the point where we're solving this, you realize we're going to be replacing sines, cosines, tangents, all the trig functions with things that look like that, which means we are automatically going to get a rational function. And it's an absolute mathematical statement, all rational functions can be integrated. I didn't say they're all easy, but they can all be integrated using nothing more than you've already learned. So that's a really, really powerful thing. And let's see, there's one more thing. Oh, at some point, I need to know what the dx is being replaced by. Remember, I'm replacing x, but I need the dx. How the heck am I going to figure out dx? Solve for x. So, doesn't 1/2 x equal the inverse tan of u? So therefore, x equals 2 times the inverse tan of u. I'm going to erase this part here. So what is the dx? Well, derivative of inverse tan, that's not a weird one. Won't that just be 1 plus u squared right there? And then 2, and then I have a du. And that's the final piece. I'll write it over here. Have these written somewhere where you can access them, so you're not having to constantly go back. Because, to be honest, these don't come up a lot. These are not like a lot of your other antiderivative formulas where you remember all your antiderivative formulas that you use, right? You don't think twice about the ones that you use. This is very obscure, but it is the only way the problem can be done. So, you always start the same way. You say, let me start with exactly this substitution, then all of those are true. Please don't rederive these. No. That was the whole point of this, is we derived them, so now we can use those forevermore. Now, there is a little bit of an issue. When I get all done with this problem, at the very end of the problem, aren't I going to have functions of 1/2 x? Because that's my substitution. Does everybody see that?